So this video is part 2 of chapter 7, and we're going to talk about the forcing functions and first order circuits. Not really that kind of forcing function. It says psychologically tuned to reinforce an important skill, holding down the trigger. No, different forcing function. Okay. Anyhow, next slide. So before we actually talk about the circuits, we have to talk about the math behind it, which are these singularity functions that we use a lot in circuits. These are really, really useful. Allows you to really understand what's happening in a circuit, and they're good because they are ideal models of what you do to circuits. You turn them on, you pulse them, you ramp up something, so they're very appropriate. So they're also called switching functions, especially in electronics and engineering. But they are functions that are discontinuous, or they have derivatives that are discontinuous. And so discontinuous means that they have an abrupt or sudden change in their value. So the three that we are going to be looking at, which are not all inclusive, but are three that are appropriate for electronics, are the step function right here. So you can see why it's called probably a switching function, because it's off and now it switches on. And right now it's a unit step function, so it has amplitude of 1. It could be volt, it could be current. So this is a unit step function, time on the horizontal axis. This is called an impulse function. You can think of it as pulsing a circuit in a very short with a very short in time pulse, but ideally and mathematically it's this impulse right here that has no width at all. It actually has area of 1, which we'll talk about in a moment. This is also called a Dirac delta function. It has some very useful properties. And then we have a ramp function. So we have discontinuities at 0 in all three of these cases, so that's what makes them a singularity function. So let's look at the unit step function first. So the unit step function is defined as right here, 0 for time less than t equals 0, and 1 for time greater than t, and so it's plotted right here. So you can also shift it in time, as we have done here, and then it's described via this equation up above. So notice, and some people tend to mess this up, the negative sign right here. The unit step at shifted in time to begin at time t0, you write u at t minus t0. So if you think about this definition, like if this was 2 seconds here and this was 3 seconds here, so what occurs at 3 seconds? You have 3 minus 2, and that would be 1, and you would be in this regime. So for some reason this minus sign here confuses people, but if you plug in a number and think about it, you see that this indeed is the math for this unit step function that's shifted in time and begins at time t0. Likewise, we can shift it in time and begin it at a time less than t0. So you have it shown here mathematically. So how that relates to circuits, you could have a voltage that's off before time equals 0 and on at time greater than t0. So we can write that mathematically now with our step function as there it is, v of t equals, and you have the amplitude and then times the unit step function. So the unit step function right here is telling you when it's turning on. It's turning on at t0, t equals t0 in this case. And the amplitude right here is v0, and we can write it like this mathematically. And this is much more convenient, it turns out, than always writing the two conditions explicitly like that. So equivalent here, v0, oh, okay, t0 is appropriate here, but actually they're showing at t equals 0 right here. So v0 times u of t, or the unit step function, is equivalent to a switch closing at that time and the voltage turns on. Little intuitive there, makes sense, right? But now we have a mathematical notation to express what's happening. So it turns out that the derivative, going back one, let's go back 2. If I take the derivative of this function, derivative of something horizontal is 0, right? Derivative of this is 0. This portion here is 0. This portion here is 0. But the derivative right here at t equals 0 is undefined. So at that discontinuity. So if we take the derivative of the step function, which is what we've done here, we get this kind of a result. So we define this derivative of a step function to be called the impulse function, also called the Dirac delta function, because this little Greek symbol right here is called a delta function, or a delta. It's a lowercase Greek letter delta, as opposed to the uppercase. This is the lowercase. And perhaps you'd recall that an uppercase delta looks like that, but a lowercase delta looks like that. So this is a delta function, also a Dirac delta function, and this is how we plot it. It has infinite amplitude, because remember we are looking at a discontinuity of a step function, so it has infinite amplitude. That's how we define it. The unit impulse function or delta function is 0 everywhere except at t equals 0, where it's actually undefined because it goes to infinity. It may be undefined at that point, as shown right here, but it has an area. So if you integrate the delta function from infinitesimally before 0 to infinitesimally after 0, which we write by 0 minus, which means just before 0, and 0 plus, which means just after 0. So if we integrate this whole thing there, and remember it has no width right here, but it has infinite height. So if we integrate this whole thing in that infinitesimally small area centered at t equals 0, we will find that the area of it equals 1. And we can use that fact to say that the impulse function has certain strengths or weight. So I can say 10 del of t, I can say 5 del of t plus 2, minus 4 del at t minus 3, and so delta. So these delta functions then can be drawn with different heights or different strengths, which corresponds to the area or the strength of the delta function. So far that's well and good, but how do these delta functions affect other functions? So what you do is you can multiply some other arbitrary function, just pick your function, anything that you care about, and multiply it times a delta function and integrate the whole thing between two values, a and b, whatever it is. But recall that this delta function right here is only has a value at time t0, and everywhere else it's 0. So when I integrate this, I'm really saying the function right here only has value at time t0, and so it's just a function evaluated at some discrete time, which would just be a constant. So therefore it comes out of the integral, and we already know what the integral of this is. It's 1, and so the net result is integration of function times an impulse function. We will obtain the value of the function at the point where the impulse occurs. So this property is called sampling or a sifting function. I always called it sifting, but sometimes it's called sampling. And it's actually really, really important, not only in this electronics course, but when you take communication or systems theory, you will see how an impulse function is used to move signals around in frequency space. So this is the sifting property of the impulse function. So the ramp function, every time I change slides I lose my pen. The ramp function is obtained by integrating the step function. So if you integrate 1, if you integrate 0, you're going to get 0. But if you integrate 1, where u of t equals 1, then you're going to get t, right? So if I integrate my ramp, I'm going to get 0 for times before 0, and t times u of t t times the step function for t greater than 0. So that's how we define the ramp function. And here it is drawn out. You can also shift it in time, just like you can shift the step function around in time, or the impulse function around in time. So you can shift it around. So keep in mind that impulse, step, and ramp functions are all related by differentiation, which means they're also all related by integration. So I have my step function right here, which is the derivative of, my impulse function here, which is the derivative of the step function. And I have a step function, which is a derivative of the ramp function. Likewise, we can go the other direction and do integration. So you go up, integrate one way, differentiate the other way, but these three singularity functions are all related to each other. So let's do some examples. In this first example, I want to describe mathematically what's happening here using step functions. So if I look at that, it's really a step function that turns on right there, which is at 2. It turns on at 2, which is not mu, but it's just a u at t minus 2. But it goes on for infinity, right? So if I add that together with another step function that's in the negative direction and does that, so a negative step function, and I add these two together, then I can cancel out, right? So this other time occurrence is at t equals 5, and you could say that this is, and the amplitude is 10 here. The amplitude down here is, we could say that that's minus 10. This one is a 10, minus 10, t minus 5. And so we can add those two up, because graphically you can just see what's happening here, right? This is at 0, this is at 0, and this is at minus 10. And I gave this step function a negative 10 amplitude, and I can add these two up, and so I get the final answer for, this is voltage as a function of time, equals 10 u at t minus 2 minus 10 u at t minus 5. So you add those two up, these two cancel out right here, and you go back to 0, and you get the shape of this. It actually has a name for it, which we'll learn when we do Fourier series next function. It's a rect function for rectangle. It's a rect function. So it's going to be important when we do Fourier series next semester. So anyhow, so you can add those two up. Now there's nothing I can do with these two step functions that are at different points in time. So the only thing I can do, the only simplification I can do from here is say 10 u of t minus 2 minus u at t minus 5. So that's the only simplification that I can do. So we recall also that the dv dt, or the derivative of the step function, is an impulse function at the same place in time. So we can apply that to see what is the derivative of our voltage function. So we can go ahead and do that. So if we just take the derivatives of this and this, dv dt will equal, so the amplitude of this first one is 10, and it's going to be a del at t minus, t minus 2. By the way, people say del for that delta function, and it's minus 10 del at t minus 5. And so we take the derivative, we get that, and so if we were to plot it, it has strength of 10. Our delta functions have strength of 10. We have one here, and we have one here. So, okay. Here's two more to try. Let's write there. Well, actually, it shows that this is I of t occurring right here, and this is the integral of I of t, which I can see integral of a step function is going to be a ramp. I could probably just by inspection write down the ramp here, but let's write the expression of what's happening here first. So I see, just like the first problem, I see a ramp that occurs positively here. I see one that must subtract here, but it's got to subtract, okay, true, so it will subtract here. And then I see one that has to bring us back to 0, so I see one more step function that has to occur probably back from 0 back up to here. So to bring that one back down. So this is at 10, up at 10, this is the 0 line right here. And these are the three that I have to add together. So I would say I of t by inspection is 10 step function that occurs at 0. I could say t minus 0 if I want, plus minus 10 step function that occurs at 2, plus a positive step back up with amplitude of 10 that occurs at t minus 4. So I can pull the 10 out if I want, no problem. I of t equals 10, and then I have u step at 0 minus step at t plus 2 plus step at t plus 4. So the step is at t plus 4, so I write t minus 4 right there. So the integral of a step is a ramp. So integral of I of t equals, and I can do this by the math, so I'll just pull the 10 out, and it will be t, do I want to do it that way? Yeah, t u of t, we'll do it that way, minus, careful here, t minus 2, t minus 2, and then something that cancels it back out again, plus t minus 4 step at t plus 4, which equals, this by definition is a ramp at t minus a ramp at t plus 2 plus a ramp at t plus 4, writing the minus. So that should give you the answer, and it's a ramp. Now I did it by my definitions right here, integral of, I did it by the definitions of integrating a step and getting a ramp. I could by inspection also say that I see a ramp here at 0 going up, and then a ramp that cancels it going down, switches the direction here, and then another ramp, because it would continue, that switches it and brings it back to here. So I could by inspection, visually looking at this, have written down this final answer, but I did it with the formal mathematical way. But actually, as I'm looking at that, I think that that's not right, because I think I made a mistake. So let's check that real quick. So this would have been a ramp up, and if I canceled it with an equal ramp down, it would have been back to 0. So I have to cancel it with something twice as high. So I think I have a mistake in here. Yes, I do. Way back here. So if I did this plus this, I go back down to 0, right? But I have to go down twice as high. I have a 2 missing, because I have to go down 10, I have to go down 20. So I do have a 2 missing right here. Hopefully everybody sees that. Yes. And then it would come out to be okay. Yeah, all right, that makes sense. I had to think about that for a minute. Ramp up, then one ramp down puts it back at 0, and then one takes another ramp to bring it down this way. Okay, good. One more example, I think. I like all of these singularity functions. So we'll do one more example. This is called a sawtooth function. And there is more than one way that you could come up with a solution for this. So let's look at our first method. And so our first method, we recognize that making this shape could be a ramp plus a, well, the beginning is a ramp plus this equals that, and then we could add one more. A ramp plus a ramp equals that, and then we could add one more step function and get rid of that part. So that's the first way that we could look at it. So we can go ahead and do it that way. So we get, draw a little bit smaller right here. We are looking at getting this ramp plus this ramp, and that's going to equal this ultimately, which occurs at 0 and 2. So this is a ramp at 0, and this one is a, oh, and what's the amplitude of it? It's the slope, right? So I have 10 and I have 2, so the slope is 5. And then we want to negate that, so it's going to be a minus 5 ramp at time equals 2. And then we get that result, correct? Oh. And so the only other thing that I have to do now is make this part come back down to 0. So if I want that to come back to 0, that would be a minus u at t at time equals 2, but the amplitude is 5, so it must be a 5 right here. And that should be the pictorial observation way of finding, except that maybe this amount is 10, not 5, so this should be 10. Okay, that's the pictorial way of finding what v of t is. So that's the first method. The second method of perhaps attacking this problem could have been a multiplication of two functions. So I could have multiplied a ramp function and a step function. By the way, a step function is also called a gate function. So I could have said, this was method 1. Yeah, so then we have to negate that. So method 2 is noticing the multiplication. So in that case, I see that v of t could be the ramp. So 5t, by definition here, u of t, that would be a ramp, right? Minus 5u of t minus 2. So this is the ramp. This is not quite, no, oh, because it's multiplied, because we multiply it, right? So multiply that, because what happens here, we have this ramp going on, and then we have a step to bring it back down. We have a step, and then we have a step which comes out to be this, right? That's what this part is, right? It's a step 0 to 2, so it's defined right there, and then we're just multiplying it times the ramp. So the ramp right here is existing. So so we get this solution instead. And then if we do the math, we will see that this was correct. It's this. Okay, so I have a ramp times a step, so the step defines the time when it's valid. So now I go ahead and do the math right here. 5t u of t minus, this is 10. Let me pause for a minute and fix what I just did because it's too messy. So I am going to pause. Okay, so I rewrote it there so it doesn't look as messy. So what we have here, just as I said, is we define this ramp 0 to strength 10, and I multiply it. It's multiplied, or here's our step function, and then I'd multiply it times a ramp, and so I will get that shape back here, that sawtooth shape. So now I just need to do the math right here. So I have 5t u at t minus 5t u of t minus 2. And so I recognize this by definition of being a ramp. So that's 5 ramp at t. But this is not a ramp right now because I don't have t minus 2 right here. So I cannot call that a ramp. So we're going to play a little trick here. And I'm going to have 5t minus 2 plus 2. So that is still 5t, correct? And I still have u t minus 2 here, or step at t plus 2. And so that's 5rt minus 5. And here's where I do my little trick. R t minus 2, and then I have this other 5t minus 2 times u of t minus 2. 5, so I'm taking this part right here, 5t minus 2 times this, and then the other one is this times this, which is minus 10 u t minus 2. Okay, so that's 5r ramp at 0 minus 5, and now this is officially a ramp. Whoops, should just have been 5 right there. So now this is officially a ramp at t minus 2. I think there's a mistake in your textbook here. No, there isn't. So it's a ramp at t minus 2 because this is good. This is by definition. And then finally the step at t, step t minus 2. And that's exactly the same result we had before. So one other one that you could do is you could also observe, looking at the third one, that it's a ramp times a step. This one is a little bit trickier, method 3 from your textbook. So this third method, number 3, is going to look at the fact that you could do another multiplication. You could multiply the ramp right here, the ramp, which is r at t at 0, and you could multiply it times a step function that goes the other way. So times a step function that doesn't go this way, but the step function instead goes this way. So if you multiply these two together, this is 0 times that, and then this number times 1, and then back to 0 here, you will indeed get that sawtooth out. So how do we write that? How do we flip over our ramp? So to flip the ramp, we still observe that, well, actually you just change the signs, so it's completely the other way. So this step right here would be u at minus t plus 2. So a flipped ramp goes that way. You just reverse all of the signs. So that's our flipped ramp. And you can check it. I can say that this is at time 3, this is at time 2, this is at time 1. So what happens when I'm at time 1? At time 1, I have the value of 1. So if I put in a time 1 here, that is certainly the domain where this step function is evaluated to be a 1. So that's okay. So our third method is to recognize that we can have ramp at t times u step function, flipped step function, which goes this way. There's our flipped step function. So then we can play some little bit of tricks. The fact that u at minus t is the same as 1 minus u of t. That's what it is. So we can replace u at minus t plus 2 by 1 minus u t minus 2. So we make that substitution over here, and so when we make that substitution, we get v of t equals r of t, and then times 1 minus, oh, I forgot all my amplitudes in here. Okay, everything was a unit here. Should be a 10 out, 5 out. Yeah, 5 out front of everything here. 5. So so substitute that back in. U at t minus 2. Then you go ahead and you distribute all of that out. 5 r of t here minus 5 we have to do the same thing that we did here. So you have to do the same math that you did right here. Okay, so this math is the same thing that we had to do up here to get to make this turn into a proper ramp function plus a step function. So you will do that same math that you did right there. But anyway, in all three cases, whether you look at visually summing up things this way, or whether you recognize that you can multiply two things together and then do some math, or multiply this with the flipped step function, these same three ways of looking at it give you the same three answers. So more examples using impulse functions. So here's two problems that textbook says evaluate these two integrals, but you know that notice that these integrals are functions times delta functions, and here's a function times a delta function, and here's a function times a delta function. So when you see something like that, you actually don't even have to worry about the integration limits, because what it means to do is everywhere this function is 0 except at t equals 2. So all that means is that you do t squared plus 4t minus 2, and you will evaluate that at exactly t equals 2. And so you do that and you get 4 plus 8 plus minus 2, and that answer will be 10. So that is the definition of the sifting property of the impulse function, is that when you integrate a function times the impulse function, it's just the value of the function at the value of the impulse function. So similarly, for this problem right here, you have to break it up into two different parts. So this function is only valid at t equals 1, so you'll have e to the minus 1 cosine 1, and then this function will be only valid at t equals minus 1, so it will be e to the minus 1 sine of minus 1. And So just a matter of evaluating that at this point, and it will come out to be 0.1988 minus 2.2873, which will equal minus 2.0885. These should be, this is time, but in your calculator, make sure that that's in radians, not degrees. Okay, so that's the sifting property. That's probably enough for this YouTube. This chapter has lots of content and is worthy of more lecture material and examples. This is a crucial, critical chapter for us. So I'm going to make a different YouTube to actually apply our step and impulse functions to our RC and RL first order circuits.